We understand that the traditional statistical analysis solely depends on the data and does not consider the prior knowledge about the environment. This works perfectly when we have sufficiently large amount of data available. In reality, we may not always have a large amount of data and might already know some details about the problem we are trying to solve. It is best to utilize the prior knowledge we have along with the data. This can be achieved using a concept called Bayesian inference. Before we try to explore Bayesian inference, we should first understand what Bayes theorem is. Then, move to exploring Bayes inference in detail with an example in Python. Bayes theorem is a mathematical way of calculating the probability of an event based on the prior knowledge of conditions related to that event. For example, if we need to calculate the probability of event A, given that we have prior knowledge of event B, we need to understand the terminology here. Probability of A given B refers to the posterior probability, and probability of B given A is the likelihood, and probability of A is the prior knowledge we have about the event occurring, and probability of B is the marginal likelihood or evidence, the new information that the data is providing. So, Bayes theorem helps us calculate the probability of event A based on the data we have. But the question that naturally comes out is, as we have the prior knowledge of event A, then why do we need to calculate the probability again based on the data we have? The answer is simple. The prior knowledge about the environment or event is more like a theory. For example, the probability of head when we flip a coin is 0.5, which is true and tends to be 0.5 when we run sufficiently large number of experiments. However, if we only try it a few times, the outcome might be a bit biased towards heads or tails. Bayes theorem helps in balancing this. Helps in calculating the probability of an event by considering both the prior knowledge about the event and the data. Bayes inference is just Bayes theorem in action. The formula is same as the Bayes theorem, just that we are using a different terminology. Theta refers to the prior knowledge or hypothesis, and D refers to the data given. In some of the advanced applications, calculating the probability of data is difficult. Hence, this formula can be simplified to remove probability of D, which makes the posterior probability proportional to the likelihood multiplied with prior knowledge. Let's take a look at an example in Python. For this example, we assume the coin is fair with the probability of head being 0.5. We generate a probability density function with prior alpha and beta as 10, which returns a bell-shaped curve with center at 0.5. This probability 0.5 is the prior knowledge we have. Let's now simulate the coin flip about 5 times, which resulted in 3 heads and 2 tails. Please note that this could vary if you run this code for yourself. This makes the maximum likelihood estimate as 0.6. However, we know that the coin is fair and we have very little data. We can calculate the posterior probability or maximum a posteriori using Bayes theorem. It would result in 0.52, which is much closer to the original belief. But flipping coins for just 5 times might result in biased data. Let's now simulate the coin flip for about 100 times, which resulted in 60 heads and 40 tails, which gives a maximum likelihood estimate of 0.6. In this case, posterior probability would be 0.58, which is moving towards 0.6, the maximum likelihood. As the size of the dataset grows, importance of prior belief would be reduced. This simple mechanism, balancing the prior against the data, explains how we prevent overfitting when the data is scarce. It is the mathematical intuition behind regularization. But so far, we have only looked at a simple coin flip, a single variable. What if we want to classify something complex, like an email? An email has thousands of words, and each word changes the probability of it being spam or not spam. Calculate the dependencies between all these words is computationally impossible. So, we need to make a naive assumption to solve it. This leads us to one of the most effective classifiers, the naive-Bayes classifier. And this is what we are going to build from scratch in the next video. If you prefer reading, a link for the detailed companion blog post and Python notebook used is in the description. If this video helped you understand Bayesian inference, hit that like button and consider subscribing to continue to decode the complexities of machine learning. I will see you in the next one.